Okay, so for 4.8, this is part 1, okay? We're going to talk about, well, 4.8, part 1 and part 2, we're going to talk about graphing polynomials. For 4.8 part 1, I'm going to give you a couple of aspects of how to graph a polynomial, and then 4.8 part 2, I'm just going to give you another additional aspect. So now that we've been talking about polynomials, you have a sense of how the end behavior looks. You have, so I'm going to write this. We know end behavior. We know how to find zeros. We know how many number of zeros there are. Zeros, okay? And of course you know how to plot points. Okay, so as you are building these resources of how you understand polynomials, it gives you a better sense of how all polynomials look, okay? So what we're going to do is we're going to add to this idea, okay? So we're going to add 3 more concepts today. We're going to talk about, well, we've talked about x-intercepts, okay? So that's already finding zeros, which we'll talk about more. Location, the location principle, which is really not more than what you know about x-intercepts. Okay, that's terrible. Let me erase that. So it's just an additional perspective on x-intercepts, and then also turning points. Okay, so let me go ahead and talk about this. Okay, so let me go ahead and give you an example. Let's say we had a function, another polynomial. It is f of x is equal to 4x to the third plus 28x squared plus 21x minus 18. Okay, so a couple of things. Just looking at this degree, third degree polynomial, I know it's going to be an S-shaped curve of some sort. So it'll have opposing end behaviors. Okay, so I have to keep that in my mind. The next thing is I know there's going to be 3 number of zeros. Okay, so I'm going to put a little note here. Maybe I'll use a different color pen. So I know the end behavior will be something that looks like this or something that looks like that. It'll be opposite end behaviors. I know the number of zeros are going to be 3. Okay, whether they're real or complex or whatever, I don't know. But there's going to be 3 zeros because of the degree 3 here. I can certainly plot points, you know, and make a little t-table if I need some additional information. So I'm going to see if I can try to find the zeros, okay? You can find the zeros by trying to do a couple of different things, okay? Let's just go ahead and let's just start with the first option. If you have access to a graphing calculator or Desmos, you can graph it. And if you graph it, you'll be able to see that it is a graph that intersects the x-axis at three places, which tells me that there's going to be 3 real zeros, okay? Another way you could do is the P's and Q's. I don't know if you remember that. It's using the ratio, so you just find you have P and Q factors of the last term, all right, and a sub 0 over the factors of a sub 1, okay, this coefficient here. So what that means is the factors of negative 18 we have are plus or minus negative 18, plus or minus 9, plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. You have all of these different combinations, okay? And then also divided by plus or minus 4, plus or minus 2, and plus or minus 1. So in this case, it's not very helpful because there's a lot of combinations. Like what it's saying is that 18 divided by 4 could be a root. Negative 6 over negative 2 could be a root, which is negative 3. Positive 1 over negative 2 could be negative 1/2 could be a root. So there's a lot of options that you can test out by synthetic division. But what I did was I happened to look on the graph, and when you have one that you're going to have to do without a calculator, you won't have nearly as many of these options, so don't worry. But in this case, I was able to see that it looked like there was an intersection at negative 6 over positive 1, okay? So I'm going to just test it out to make sure. So I'm going to test it by using synthetic division because I wonder if negative 6 really is a root. So I'm going to set up synthetic division, or you can use long division if you like. and just test. And our goal is to see if we can come out with a remainder of 0. So if I take the 4 down, that gives me negative 24. 6 times 4, negative 6 times 4 is negative 24, that's negative 3. Negative 6 times negative 3 is positive 18, and yay, thank goodness for technology, or you could just plot it and see, okay, using a t-table or whatnot. Looks like negative 6 is in fact a root. So in fact, this is a root, and this is going to be the leftover polynomial. So in other words, f of x, which is 4x to the third plus 28x squared plus 21x minus 18, can be factored as x plus 6, times 4x squared plus 4x minus 3. All right? And at this point, you have a couple of options that you can do. You could go ahead and try to factor this if it's factorable. You could try to use the quadratic formula, but go ahead and see if you can figure it out, because I'm going to save some time really quickly and tell you that if you finish this, you'll find roots at negative 6, and let's see, what are the other ones? I believe it's negative 1/2, negative 1.5, and 0.5. Okay, so in other words, negative 3/2 and 0.5. You could double check. I don't have Desmos in front of me, but you can see if you can try to factor it or put it through the quadratic formula or completing the square, any of those strategies to verify that these are the roots. Another thing that we also can tell is that you have a y-intercept at negative 18, if that helps you. But really quickly, I was able to graph it, and it looks something like, I think it goes up, down. It's pretty extreme. It's a really narrow graph, actually. Should make this really high. It goes really high up here. So there was a couple of things I was able to see, that there was a root at negative 6, negative 1.5, and I think this is 0.5. You could double check. Here is 0, 18 at negative 18, and actually it goes all the way down here, and it goes all the way up here, actually. I have it written here that there is a peak here at negative 4.25, comma 91. So it's way up there, and then this point right here is at negative 0.411 and comma negative 22 something, negative 22.179. Okay. All right, so I'm giving you all this information because this will help me explain these two pieces of information about this polynomial, okay? So what the location principle says is that if you have a point on the graph that's below the x-axis, and you have another point on the graph that's above the x-axis, guess what? There is a 0 or a root living in between those points, okay? So that's what this location principle says. If you know that the graph has a point below the x-axis and it has a point above, so let me show you another example. Here's a point above and here's a point below. Guess what? In between that point is going to be a root, okay? I don't know if it's a surprise or if it's just kind of makes sense to you, but that's what the location principle discusses. That's basically what it outlines. Now, the other principle that's talked about in 4.8 is this concept of turning points, okay? And the turning points is basically where the graph turns. So it goes from increasing in this case to decreasing. This is what we call a turning point. And likewise, in this case, it's decreasing, and then right here, it turns and it becomes increasing. So here is another turning point. Okay. Later on, or actually, right now, we'll go ahead and name it. When you have a turning point here, this is what we call a local max. Okay. So I'm going to write local max because in its nearby location, this is the highest point. And then this one right here is a local min because in this general vicinity, it's the lowest point. Of course, we know the end behaviors go on forever, but just within this area, this is what we call local min and a local max, okay? So just some vocabulary to get you guys started. In terms of finding these things, like the local min and max, those are things that we're going to get to. I don't know if even in this class, but it's more of a pre-cal calculus concept. But we'll figure out how to use kind of these things and taking it to a limit to find these things eventually over time, exactly where they're located. All right?